So today I would like to talk about async programming in C# and cover this right here, task. What can we do with tasks? What is a sync model in C#? How do we use it? Why is it beneficial? Why do we need it? So here goes. I will look in the chat in case you have questions, and let's start with it. So what is a task? That's the core concept about our async model in C#. I'll also share this with others on other streams. All right, let's continue. So I hope my quality is fine, by the way. Oh crap, I forgot to change the title. I will quickly go into that. Video produce, no, not here, live. Async programming in C#. Task update. Done. All right. So what is a task in C#? A task basically means that you have an abstraction of work that needs to be done. Literally a task. A task that you would put in your to-do list in real life could be abstracted away in the same manner in C#. Something that takes quite some time, and in programming sense quite some time, is something that takes more than 0.1 millisecond, maybe 0.5 millisecond is something really that you need to take in consideration. I would start from something like 0.1 millisecond. If it takes more, it should definitely be a task. Why? So let's start with the why. Task is an abstraction for work that needs to be done. It's not an abstraction of hardware. That's the difference between a thread and a task. Task is for having a high-level abstraction of something that needs to be done. Thread is literally what it is. It's a part of your CPU. A CPU has a thread. A CPU can do, one core has one thread. One core can run one process. So when you create a thread, you can run one process. When you create a task, it might run on a new thread, maybe not, but it's not up to you. It just means that it won't block the thread that you're at. That's why we need a task. And task runs on a thread pool. That's why we need them. It's a high-level abstraction of work that needs to be done, and not to delay the main thread, that the runner thread that all other things are happening on. We can use a task to offload some work to other threads and optimize our work that way. With tasks, execution will take less time, and well, your programs will be faster simply because of that. When you are creating tasks, when you're creating asynchronous methods, you should suffix them with async. So each task should be async. Let's continue. So why is task, if task runs without blocking, why is it not the same as a thread? Task is an abstraction of work. And when you run a task, it runs on a thread pool. And when a task runs on a thread pool, it will be put to a different thread that it is currently running on at. For that reason, you will at least use one extra thread, but you might need more threads, but you might not. So with threads, you are using a new thread every time when you create a new thread, but you're not using a new thread when you're creating a new task, because it's up to a thread pool to optimize that away. Task runs on a thread pool, and there is no way of telling a task to run on a specific thread. You can run sync code on a new thread via creating threads, but you cannot do the same with tasks. So the problem with sync code is that it idles a lot, but when it idles, it still locks the CPU. With tasks, you can share CPU cores between different tasks, other processes. So if a core idles, you can use it to do more work. So with tasks, you can optimize it so that it uses it for other work. So for example, if you call API 20 times, 20 different endpoints, and if you called it synchronously one by one, you would be wasting a lot of time, because you would be waiting, let's say, a second at least to get each call, as opposed to if each endpoint was a service of its own, you could have sent 20 calls at the same time and awaited them all asynchronously, which would result in probably 20 times faster, roughly 20 times faster processing, data retrieval from them. That's why tasks, that's why you need async. Why do we need async? With async, you can use await. With await, you say something runs on a thread pool and it doesn't block. It basically waits, idles. But it doesn't lock the resource, the CPU, which runs the core, which runs the thread, which runs the code that we need. Async by itself doesn't make code async. Await does. So if you need to call await, you will have to make a method async. And again, 0.1 second or more, definitely await. As stuff like this accumulates, and you can optimize the way. Sometimes we have tasks which don't have to be asynchronous. For example, look at the following. You have task cook async, you have void play while waiting for food, you have eat async, sleep async, do something else async. In the example, I forgot to add those prefixes, but imagine that they're there. So evening routine. First, let's think if this was a synchronous code. If this was a synchronous code, you would put a pot on a cooking stove and turn it on. And then you would look at the pot till the water boils for half an hour. So you would look at the pot for half an hour in synchronous code. In asynchronous code, you would cook something, so put a pot on a stove, put a timer for half an hour, and leave it be. Then you would play video games simultaneously while waiting for a pot for water to boil. And eventually when it boils, when you waited for it, you come back. Then you eat and then you sleep. At the same time, when that happens, you can be interrupted. Somebody can come and say, hey, let's talk, and you would be able to talk. If this was synchronous, you wouldn't be able to talk. You would still be waiting for stuff to happen. That's why. So why do we need a sync task, non-async task? We need non-async task to simply await for something. The only reason why we need async is to await, is to call await. We can await non-async as well. So async just for await. To await something, it needs to be a task. And sometimes a task is like void, which returns nothing. So we have a property, a static property of a task, which is task.completed_task. So when should we async avoid? As I said, usually you have async task, but sometimes async avoid is usually needed. Sometimes. It's usually a smell and a bad thing to have async avoid. Async avoid means that it has a task within itself, but it's not awaitable because it's void. You can only await a task or a task which carries a result. So async avoid is needed because we have event handlers or we have highest level functions like main, entry point basically. So those can be async void, and that's fine because we are not going to await and use them anyways. They're highest entry points in our programs which will not be reused. We are not supposed to reuse and call event handler. We're supposed to subscribe it to some event. That's all. We're not supposed to call main from anywhere. Main itself will do what it needs, but it won't be reused. That's why we can use async void for such functions. So alright. Async from sync context. How can you run code asynchronously from sync context? Well, you just do like this. Task run, and your code is suddenly async. Task run, and you can pass in an action, a delegate, which does something. And by doing task run, you put you offload your code to a thread pool. And in fact, there are two thread pools in a thread pool that .NET has. So let's talk about it. One thread pool that the .NET has is for CPU-bound tasks. CPU-bound task is basically something that every task which runs on a CPU-bound thread takes that thread and locks it. It's the same as running sync code within a thread, within a new thread that we created. It's equivalent. It blocks the thread, but another thread, not the one that we ran it from. So it blocks a thread that it runs at in a thread pool and does heavy CPU processing. So if you don't do much on a task which runs on a CPU-bound thread, you shouldn't have called it with task.run. Task.run should be called only for something which has really heavy processing, really heavy, intense CPU-wise task. For example, to find a Fibonacci number of 30, like 13th Fibonacci number, you would need to, well, with a single core of 4 gigahertz, you would need to wait at least half a second. And so it's really heavy and it's all work. That the half a second is all work. And task run for Fibonacci of 40 further, definitely go for it. It's good. It's really efficient to offload this to another thread. So task run, calculate Fibonacci, perfect, works. Now, so if you look at the picture, when you use task run, imagine that you have big fat task, which does a lot. It doesn't just wait, but it does a lot by itself. Now, if you have something which is limited by the traffic and which mostly awaits for something, For example, if you call an API asynchronously, which returns a result, well, you don't really do much by yourself. You just wait. The heavy work is done within the server, which you call the API itself. And it might be a completely different server altogether. So by calling multiple tasks asynchronously, which call different APIs, is perfectly fine. I mean, web APIs is perfectly fine because you basically spam requests to APIs and you wait for response. So it doesn't make sense to, let's say, imagine the following. You're on your bike and you need to buy milk from one shop, then batteries from another shop, then feed for your pet at yet another shop, and you visit 3 shops. So, and some of those shops are going to be opened. Well, yeah, you buy stuff at the shops. So what you could do, synchronous would look like you buy something from first shop and then you go back home, then you go to another shop, then you go back home, and then you go to the third shop and then you go back home. Asynchronous would look like that you basically call a courier, 3 couriers, you call 3 couriers one by one, and then you wait and do whatever you want while those couriers deliver stuff for you in the time that they do. So asynchronous means offloading something to thread pool, and in CPU bound work you offload something on CPU bound thread pool, and that something is very heavy, takes lots of time processing wise. And IO bound is another thread pool, and the example is the web API calls. So with IO bound, you wait a lot. You don't do much yourself. Something else, some other server will do the heavy lifting. You just wait for it, and you wait in another thread. And if task run basically creates new threads when it does so, I mean uses new other threads, different threads when it does so, await will most likely just, share the same thread on a thread pool to do the waiting. Or maybe there will be no thread and there will be a very low level and just small interruptions, and that's all. So the one on the left, CPU bound. So don't replace task run. Don't replace await with tasks. Await for task that runs properly. I mean, the one on the right, get async, is a task. It's a method defined as a task. So the one on the left, if get async was non-async, if it was synchronous, task run would not be a good replacement for it. It would be a bad workaround. Why? Because it would reserve a thread for simply waiting. That would be a huge waste of resources. That's why task run for heavy stuff, and just async method call for waiting stuff, for something that shouldn't block. So I talked about that. Sometimes we need to say and be for sure that a task will run for a long time and a new thread has to be reserved, and we can ensure that with a property called task long running. With that, we can say that such thread, a new thread will be created, new thread will be reserved, and that's an optimization, because you might run out of threads for swapping context in your thread pool. Because when you think about thread pool in .NET, you should realize that it's one thread pool for the whole system. It's not a thread pool per your program. It's a thread pool per system. So you might end up running out of threads. Also, a while ago, I asked my colleague, if our CPU has 4 cores, well, it usually has, if it has 4 cores, that means it usually has 8 cores because you have physical and virtual core per each core. So if it has 8 cores and each core has a thread, and each thread can run a process, but not more than a process, why the hell would we ever need to create more than, let's say, 8 threads? Why? And the answer to that is because it's rare that every thread works 100%. And so by having, let's say, 100 threads, it would simply mean that those 100 threads are doing something easy, something that doesn't require their full effort to run. And 100 threads is not a waste of creating objects and doing abstractions. It's an actual useful thing. With 100 threads, you can have 100 tasks that are being awaited, for example. It would be a waste if they're all 100% used, because you wouldn't be able to use 100 tasks on 100 threads. You don't have this many, simultaneously. You don't have this much resource for processing left. So that's why you need 100 tasks, potentially, to be able to offload work which doesn't do 100% of, doesn't take 100% of CPU resources. It just takes a little bit, and so I await, and at the same time I swap my resources and mix between one thread and another. If a CPU, if a thread has something free, some free space, some free working power, then that CPU, that thread can simply be taken over. That power can be taken over by another process that I need. So sometimes we need to come back to our synchronous context from async. And how do we do that? Well, with a little hack by calling wait. So if we call wait or result, it will block the execution until the task is done. This is not a recommended approach, but sometimes we need it. Again, this works only for highest levels. This should be done on highest levels. It works everywhere, but clean approach is only valid for highest levels, because you don't want to block suddenly somewhere low level a task that you await. You want it only in high level. So every time you use await, God kills a kitten. Don't do it. Kittens are precious. ConfigureAwait false. Let's consider this situation. We are at Windows application, let's say some desktop application. So desktop applications have a thing called UI thread. When you run the application, by default, it sits and runs on UI thread. So synchronization context is a UI thread. So by default, when you await a task and the await is done, it returns to UI thread. But sometimes, well, when it returns to a UI thread, it takes some time. I mean, consider this. When you run a task, it goes to another thread, to a thread pool. And then it needs a well, and then it checks, and then the UI thread checks if the task is done. It keeps checking it, at the same time renders the stuff that it needs to render. And so when the task is done, it will need to find the thread which called it and return the exact same thread which called it. And that costs some CPU work. That costs some effort. That's not cheap. So you can make it cheap and you can ignore that, calling ConfigureAwait. And ConfigureAwait means that the task will no longer return to the thread it was called from, but it will continue running on a thread it was running initially. So if let's say UI thread ran a task which ran on thread 1 and I called ConfigureAwait false, after the await is done, the next code will run on thread 1 and not on a UI thread. This case is useful for optimization, and it's not so useful when you need to update UI afterwards. If you need to update UI, it needs to happen on UI thread. So for UI, ConfigureAwait false does not work. So I talk about UI thread, and now how do you do synchronization, and how do you properly await, and what you should do and what you should not do. So instead of task wait or task result, just call await. Don't do the one on the left. If you need to wait for many tasks, when any, call when any, not wait any. When you want to wait for all tasks, just say when all and not wait all. And when you want to delay something, just do task delay and not thread sleep. All the stuff that's on the left deadlocks your application, and you don't want to waste your resources for deadlocking. Asynchronous programming requires a different kind of exception handling because you cannot catch an exception if you don't await it. Consider the following. You have a try and a catch. You try to catch exception of a synchronous method that you did not await. What's the result? The result is that the exception will not be caught, and thus your application might crash. In .NET 4.5, tasks which are not awaited and which fail don't crash your application. Before .NET 4.5, it would crash your application if you didn't handle exception. So how do you handle it? You handle it this way. Well, it won't be handled. You handle it this way. You need to await for a synchronous method, and then you handle it. By awaiting, you get an exception, exactly the exception that was thrown at you. So other way to handle exceptions with async is by waiting for them. You can just say wait, and it will also throw an exception. You will also catch an exception if you wait for something instead of waiting, but that exception will not be exactly what you expect it to be. If you handle exception of something that you waited for, you will get an aggregate exception. Aggregate exception is an exception which has other exceptions within it, meaning an exception which has a collection of exceptions within it. So you will need to inspect other exceptions to know what happened, what went wrong, and it's not a direct message for what went wrong. So this is the exception, and as you can see, you have one exception as a counter. If something went wrong, once, you will have one exception nested with an aggregate exception. If something went wrong more than once, well, the counter would be accordingly 2, 3, or more. And a thing to note, if you call aggregate exception flatten, sometimes you have exceptions which are nested. So aggregate exception can have other aggregate exceptions. And to have just a single list of exceptions, you can call flatten method of aggregate exception. And it will return a single list of those exceptions. So if I await, I catch a normal exception. So there is no magic here. Sometimes we cannot handle exceptions. I mean, sometimes we have tasks which we fire and forget, and it's quite hard to handle those. So how do we handle them? There are global error handlers which can handle exceptions in general which aren't handled. But if an exception, if a task throws an exception, if a task which isn't awaited throws an exception, it should probably have a try catch of its own, because it's a big enough thing that should have a life and error handling of its own. But if you want to handle it globally, you can do the following. Let's say just log. So unhandled exception, you register unhandled exception, and then you just implement how you handle it. Sometimes you could even do something that basically says, so a task failed, and if a task failed, you can have another task which handles a task which failed. Also works. And sometimes you need to handle cancellation of a task. You fired a long-running task, but something went wrong and you want to cancel it. So you can cancel tasks the same way you cancel threads, with a cancellation token. To get a cancellation token, you need a cancellation token source. And so by passing cancellation token into a synchronous operation, you can cancel it. So when you call cancel method from cancellation token, it will cancel a task. When a task gets canceled, cancellation token will have a properties cancellation requested set to true, and so if it is, you can throw an exception operation, cancel exception. Or you can just say cancellation token throw if cancelled, and if you call that, it will throw the following exception. The result will be that the exception will have a reference to a task which holds metadata about that task, meaning which it will say if task managed to complete, if task was running, if it was cancelled, if and so on and so forth. So this is the exception, and by default, a task which gets cancelled doesn't throw an exception. You still need to call the exception by yourself manually. And this is all that I wanted to talk about in this lesson. Do you have any questions? If you do, please ask. If not, so be it. Thank you for watching. Bye bye.